Hello everyone, and thank you for joining us in today's presentation. The webinar today will cover one of the latest tools that was added to ETAP, the UDM Scope Plot View. This recently added tool allows for a more flexible and efficient analysis of the results for several types of studies in ETAP. Our agenda today will include the introduction of the UDM Scope Plot View along with several application examples where some of its features will be highlighted, such as the field measure data import for parameter estimation and tuning, also the instruction file preparation for results comparison, as well as many other features. And towards the end of the presentation, we'll discuss about transient stability oscillations and damping conditions and some of the challenges that define the need for this analysis tool. So let's go ahead and get started. For our first example, we're going to demonstrate how the UDM Scope Plot View can work as a very powerful tool for dynamic studies where parameter estimation and tuning is to be performed. In this case, we have some field measure data that we need our digital twin in ETAP to respond as closely as possible. For that, we first need the file with the recorded data in the required format, simply having the time column. And if we don't have the time column available, the UDM Scope Plot View can recognize and detect that and give you the capability of plotting the signal even without the time column. And of course, we need the plot data, the actual measure data from the field that we want to plot in the UDM Scope Plot View. So as you can see, this would be the old method how you should do it if you didn't have the UDM Scope Plot View, as I'll show you in a second. Simply plot and compare the results that are generated from ETAP CSV files from UDM scopes. We have a very large system to which we're going to perform several transient stability simulations to try to match that response that we just saw from the field measure data. But first, let's access UDM so we can have access to the UDM Scope Plot View. For that, we simply need to open any of the UDM models in your system. And once you are in the UDM model graphic logic editor, in the simulation tab, you can open the UDM Scope Plot View. As you guys can see, the UDM Scope Plot View is a separate window, it's an independent window that can be opened even if you don't have any UDM model open in your system, only with the ETAP window. And it is comprised of several tabs, one data source tab and 4 comparison tabs that we'll try to take advantage of in today's presentation as much as possible. In the data source tab, you basically control all the different plots and results that are being displayed and also the comparisons that are being performed and also the analysis of the results. So you can load plot databases or plot files from either single databases or from multiple plot files when selecting the test project folder, for example. Additionally, you can select the type of database, either CSV, like the one that I showed a couple of seconds ago, or SQLite, which is also supported by ETAP for UDM scopes, and also different ETAP modules like transient stability, motor starting, and short circuit for IC 61363 standard calculations. But for today's example, or for the first example that we're going to cover today, let's load the CSV file that I just showed you for the field measure data. Once that data is loaded, we can simply generate the results as we also saw in the CSV when I opened the CSV file in Excel. And we're going to try to match that response with the actual data generated by the transient stability module in ETAP from the UDM scopes in the UDM model that I'm showing right now for the Exciter. As you guys can see, we just simply need to drop a couple of scopes so we can actually generate that CSV file, that plot database file. We're gonna name this bus voltage And we're going to need one for the frequency as well. We simply generate, and this is the UDM model, the dynamic model that we're going to try to tune so we can match the response from our ETAP system. And meanwhile, what we're going to do is we're going to show you another capability of the UDM Scope Plot View, which is the plot comparison file preparation, right? For that, when we switch to the plot comparison tab within the data source tab, we have a set of a data grid, and where we're going to actually assign different plots as either benchmarks or results. In this case, our benchmarks are going to be basically the measured data from the field, right? And our results are going to be the results generated from ETAP Transient Stability module from the UDM scopes that we just placed in that UDM model, okay? So let's start first assigning our field measure data as the benchmarks, right? We're going to first assign the field voltage of the exciter of the excitation system as the comparison 1 chart 1 benchmark. For that, we simply click on assign, and we see the assignment of the comparison chart that we have selected. Now let's select the voltage as the second plot to be compared, and last but not least the frequency. And now we can see that ETAP has already finished running the calculations for our transient stability scenario, so we can simply bring our data from the CSV file generator from ETAP to the UDM Scope Plot View. So for that, we simply need to go to our project folder and select the CSV file that were just generated by transient stability, which has a specific name format, as we can see, is the element ID plus the type of UDM model. In this case is an exciter, the dynamic model that we're trying to tune, and the one where we added the scopes before. Then the UDM model ID or name, and last is the output report name. In this case, like I mentioned, is going to be the plot data from the exciter, the one that we're going to use for this first example of today's webinar. And now we need to do the assignment of the plot comparisons. Like we did with the field measure data, we need to do the same now for the results, for which first we need to change the type of plot or data plot that we're handling. In this case, it's going to be the results, as the benchmarks were the field measure data, and again the comparison chart that we need to assign this specific plot to. So for the field voltage, we're going to assign for comparison 1 chart 1 result, and for voltage we just need to switch to chart 2, and the same for frequency. Now that we have finished assigning and creating our plot comparison instruction file, we can just simply switch to the plot comparison tab, and we'll see how the data is already populated, automatically populated. And the moment we simply click on plot all this plot data is retrieved from where it's saved and shown in the specific comparison tab, which in this case is the comparison tab 1, as we have assigned to the comparison 1 here in the plot comparison data grid. So once we plot all, we simply go to the comparison 1 and we check that the results, and we can see that even though the response is very close, the response from ETAP, which is the red one, the results one, is very close. It's still not close enough to what we want for our digital twin in ETAP. So in this case, the tuning process starts, for which we need to go to our dynamic model for the excitation system or exciter, and in this case we're going to start changing some of the parameters and running the simulations back and forth until we'll get a closer simulation, a more precise simulation. So let's start with this proportional gain, and we recommend doing this sometimes one item at a time, so we know basically we're getting closer or not to the final result. Once we have compiled the model, we simply need to go and rerun the scenario. And now at this point, we have the results from our first simulation in the UDM Scope Plot View along with the benchmark. And it's time to show you one of the features that characterize this UDM Scope Plot View and why it is so powerful for this parameter tuning and estimation, which is the overlay. With this checkbox, we simply allow the user to overlay as many plots, as many results plots as they want, and we can even give different names, so you can give a distinctive name to recognize what simulation. In this case, we are running the KPKs equal 50. So we're going to add that name there and wait until the transient stability finalizes so we can plot the net set of data. And now the transient stability is completed, as we can see the icons become available, we can simply click on Plot All again, and the result should be updated in the Comparison tab. So we can see how the results are different than the first time, right? We can see the red one are the original results, the yellow ones are the benchmark, and the dark red is the results from the last simulation with the gain set to 50. We reduce that gain, and as we can see, we can maybe zoom into the scenario or to the voltage results. We can see we got closer now to our response, but still I think we need to go through another set of parameter tuning so we can get a better and more accurate result. Okay, let's do the same. And again, it seems that the proportional gain is giving us a closer, a more precise result. So let's try reducing it one more time, compiling our UDM model and going to ETAP to rerun the results. And meanwhile, we just need to go again and rename that plot so we can overlay and see the difference in the results. And now that ETAP has finished running, we can again simply click on Plot All, and the results should be updated in the Comparison tab one more time. And now we get the next set of results, which is the green plots, and it's a little bit difficult to see, but again, if we use the zooming capabilities, now the green plots are much more closer to the yellow one, which are our benchmark. So I think that we can say that we have successfully tuned our model, and now our digital twin in ETAP is closely matching the results of the field measure data. Additionally, this overlay feature it allows the user to overlay so many plots until you get the correct response, the desired response, but at the same time, we could actually plot individually here. Once we come back to the data source tab, we can plot individually the plot selections and the comparisons. So we can see this is our final response for the final set of results or parameters that were tuned in our dynamic model. We can see the frequency response, it's almost spot on, the same as the voltage, just some minor differences, but acceptable. And we can see how the field voltage, we can see how that closely matches the actual benchmark, which of course, this is field measure data with all the oscillations and the noise that produces, whereas the ETAP response represents a signal without any type of noise, but we can see how the average of that signal matches the response from the field measure data. Now, moving on to our next example, for this case, we're going to use the test system from the IEEE 3002 series of standards, and we'll be basically utilizing the UDM Scope Plot View to analyze and compare the results for a voltage impact study done in this project for different operation modes of a wind power plant. which is going to be modeled through the aggregate element that I'm highlighting right now in the one-line diagram. Such renewable plan is going to be dynamically modeled using the generic models provided by the WECC, the Western Electricity Coordinating Council. These models were recently added to our UDM library along with several other models for renewable energy systems. And as you can see, is a very complex dynamic model with different type of controllers for both active and reactive power that are generated from the WTG that is being modeled. For this case, we also have a benchmark set of files, which is basically is going to be a previous simulation that I ran with the operation mode of the WTG or the wind power plant set to voltage control, as I'm going to show you right now. For that, I need to load first the plot databases from transient stability. Here from the project files, you guys can see transient stability, voltage impact, benchmark, and we're going to load the plots. As you can see here, all the different plots for all the elements for transient stability are brought to the UDM Scope Plot View, for which you can easily generate the plots for any element that you want in the system. For this case, we're going to go ahead and perform a similar procedure to what we did for our first example, and we're going to try to match and use the plot comparison in a different way. This way, not to compare the results or not to try to match while we're tuning the model, but actually to compare the results as we change the operation mode of the wind turbine. So for this case, we're going to grab 3 signals, which are going to be the terminal voltage of the wind turbine generator, and let's assign this as benchmark, the active power and the reactive power. Basically, we're following the same procedure, first selecting the comparison tab and chart number and the type of plot. In this case, these are the benchmarks. Okay. Again, as we can see, we need to assign the reactive power to the third one and the active power to the second one again. Once we go to the plot comparison tab, we can see that if we click on plot all, they are now plot. As you can see, voltage, terminal voltage is being controlled. Once the voltage is reduced because of the voltage impact study simulating in ETAP, the wind turbine or the power plant, this wind power plant, try to control the voltage, injecting more reactive power into the system while the active power remains constant. Okay, so now we're going to move on and simply go ahead and change the operation mode of this dynamic model that, if you guys are familiar with, is controlled through the different combination of the flags. Okay, the flags are located in the bottom section of the UDM model, as you guys can see here with some description. And now that we have tested or we've shown the results for the local voltage control, we're going to move on now to the reactive power control. So for which I need to modify this to 0 and the rest of them to 0 as well. Okay, we simply need to now compile the results, compile the model, go to your ETAP system and run the calculations. Okay. While ETAP is running, we can go back to the UDM Scope Plot View, and again in the data source, we're going to select now our results, the ones that we're going to compare against our benchmark. Okay. Again, we're going to bring the data from the SQLite plot databases from transient stability. Let's simply select, this is the one that we just run, TS underscore VI as in voltage impact underscore 2. Let's load it. And we can see we have now hundreds and hundreds of plots available here in the UDM Scope Plot View, but we're going to focus in the plots from the wind turbine generator. Now, like we did with the first example, we need to change the type of results or the type of plot to results, and again assign it to the correct comparison chart. The voltage, the terminal voltage is assigned to comparison 1, chart 1. We can see we can generate the plot before we assign it. Then we have the active power assigned to the chart number 2 and the reactive power assigned to chart number 3. Okay. Now when we move on to the plot comparison tab, we can see again that this is the plot comparison instruction file has been generated automatically as we did the selection in the available plot data. And the moment we click on plot all, we can see the results compared in the comparison 1 tab. So you can see the two differences. The yellow one is the benchmark. As I explained earlier, the operation mode of the wind turbine generator was set to voltage control. Therefore, we can see how the terminal voltage is actually being controlled through the reactive power injection. Whereas for the result section, or for the result set of the final run, the operation mode was set to reactive power control, which, as you can see, is kept constant to 0, because let's say, for example, we don't want to simulate any reactive power injection from a renewable sources energy plant. And again, also the active power is unaffected. So now we can go ahead and move on and additionally test another operation mode, which is nothing but the power factor control mode. And again, we simply need to change the combination of flags, compile the model one more time, and rerun the calculations. Now that the model has been compiled, we can simply go ahead and rerun the transient stability scenario. And in our UDM Scope Plot View, again, we're going to make use of the overlay feature, but this time we're going to rename it as power factor control. Now that I finish running the calculations, we can simply click on plot all and go ahead to the comparison tab, and we can see the results. Now the power factor control mode is set to, we can check in the UDM model actually, is set to actually a power factor of 0.98 or 98%, which, as you guys can see, if we want to keep the active power constant, we need to actually start providing some reactive power, as you guys can see here in the dark red plot. And therefore, since we are reacting or injecting more reactive power, the actual terminal voltage is slightly higher. And of course, once we apply the voltage impact scenario or simulation or disturbance in transient stability, we are not controlling voltage as we are controlling the power factor. We are keeping the power factor constant. Now that we have gone through this comparison process and comparison instruction file preparation, it's logical that we don't have to go through this process again. And that's the reason why we allow you to actually export that comparison instruction file that you work so hard to prepare. So next time you could actually just simply import it and get your results, compare your results automatically without having to actually set up again the comparison instruction file. So we can simply click on export, and this will direct you to your project folder. So we can actually put and rename it as webinar instructions. And the comparison instruction file has been exported successfully. Okay, we can clear the list, we can clear the plot, and simply import it again. Select it and import it. So we have all the results and all the comparison instructions that we have set up previously, again, by bringing or by importing the existing instruction file. And also in this case, that we have compared the different operation modes of the wind turbine generator, I want to import a different comparison instruction file that I have previously created to show the versatility and how powerful this can be. right? For example, in this case, we are simply comparing 3 different signals from the WTG element, but we could actually bring or compare signals from several other elements as long as we have the plot databases from transient stability or from any other module that we are selecting to compare the plots for. In this case, we have not only the wind turbine generator plots, but also some plots for the main synchronous generator of the system to see the behavior for the different operation modes of the wind turbine generator, how it affects the behavior and the response from the main generator in terms of active power, reactive power, field measurements, and also one of the big motors, one of the larger loads in the system. Once we click on plot all, we can simply go to the different comparison tabs. This is the one that we have already checked, and the next one is the one for the generator, active power, and also mechanical power from the actual governor system, and the reactive power, the field current and field voltage, and the response from one of the big loads of the system. So we can see how with this tool we can actually compare not just the results for one element at a time, but several elements, several signals at a time for different operation modes of our wind turbine generator. And as I just showed you, we can actually import previously created instruction files, allowing us to perform a more efficient analysis of the results. Now, for our next example, we're going to perform a different type of study. Motor starting studies are essential in industrial power systems, as they serve several purposes, like, for example, voltage drop or voltage impact due to the starting of a motor, motor feeder sizing, starting acceleration time of the motor, or even the stability evaluation after a large motor is starting our system. And for each one of those purposes, ETAP offers a solution, right? However, today with the UDM Scope Plot View, we'll learn how we can combine all those solutions to make the analysis of the results even more efficient, okay? So first of all, I'm going to run a quick macro of scenarios that I have already prepared for this presentation, where we're going to run basically the starting of a couple of motors in our system in 3 different modules or 3 different type of studies. The first one is the motor starting through transient stability, then through motor starting module, but using the dynamic starting analysis, and third one is going to be the static motor starting through the motor acceleration module in ETAP. So while ETAP is running in the background, let's go ahead and clear our tool, and so we can bring the plot data right now, and I can show you how you can actually bring multiple plot files from a specific project folder. In this case, for the motor starting, let's start with the transient stability plot data first, for which we need to select the motor starting results that we just ran. Let's load that. We can see here the plot file name as TSMS, right? Now for the motor starting, since we have a couple of studies or different output report names, one for dynamic and one for static motor starting, we're going to actually load multiple plots at the same time by simply selecting the actual project folder. As you guys can see here, the project folder, the root project folder path is automatically selected, so we can actually load simultaneous output report or output plot data files at the same time. Here we have the MS dynamic and the MS static results from both output reports from both plot databases, okay? And additionally, I'm going to also import a previously created instruction file so we can see the comparison between the 3 different type of studies that we just ran, for which I'm going to plot specific signals or specific parameters like the slip, which is related to the speed, the terminal bus voltage of that motor, the line current, but also the active power from the main synchronous generator of the system, so we can analyze the impact of starting that motor into the actual generation of the system. So once we click on plot all, so we can see the different responses. Remember, the first one are the results for, or the ones at the top are the results for transient stability, the second one in the middle for dynamic motor starting, and the last one at the bottom for static motor starting. So we can see this is the slip response, which is directly related to the speed response of the induction machine that's being started. So we can see how both the dynamic motor starting, which is performed in motor acceleration module, and the motor starting performing transient stability are very similar, except for some transients that are basically related to the different dynamic modeling of other elements in the system, right? So as we can see, the terminal voltage, of course, we're having here the heavy impact of the wind turbine generator and the synchronous generator exciter, which are trying to control the voltage of the system, which of course is not considered for other statics like dynamic motor starting or static motor starting, right? Static motor starting, we can simply see the voltage impact of starting that motor. It's very simple, and that's why we don't need too much information or too much data for the static motor starting, but it basically its purpose is very simple, is to determine the voltage impact due to the starting of that motor, right? Next, we have the actual line current or terminal current from that motor. The same for transient stability. We can actually see different transients during the time simulation that are not observed in the dynamic motor starting, even though the dynamic motor starting shows a very similar waveform, a very similar behavior. We need to keep in mind that during dynamic motor starting, we do not consider the dynamic modeling of other elements in the system, only the one for the motor, the induction machine that is being started in that simulation. And last, we can see the actual active power from the generator, which of course it's also controlled or impacted in the case for transient stability by the actual governor and prime mover system of this generator, which is not considered in the other simulations as well. Now, with the UDM scope plot view, we're not only able to display or generate the results in a graphical way, as you guys can see right now, but we can also analyze the result as we've been mentioning so far. For example, if in this case we wanted to evaluate the motor terminal voltage to determine whether it falls outside of an acceptable range or not, I'm not going to ask you to go ahead and go to the available plot data tab and analyze and check each one of the plots here, which are hundreds, by the way. But instead, we can make use of the analysis tab of the tool, which provides a set of multiple filters with predetermined useful conditions, right, that check all the available plot databases and generate the plots that are violating or that doesn't meet the criteria. Okay, so we have a specific range, and once we click on or once we enable any of the filters, if one of the plots that is analyzed through the available plot data tab does not meet the criteria, it means it's outside of that range, then the tool, the UDM scope plot view, will flag you, will generate that plot for you without having to actually manually check and check the calculation and check the numbers. So for example, for this case, we can actually check the motor terminal voltage, which we can set, for example, between 110% and 85%, and try to plot the selections. And out of hundreds of cases, hundreds of plot data, we only generated two, specifically the compressor B terminal voltage, which of course it's susceptible to go below that threshold, below that range, because this is one of the motors that's being started during the simulations. However, we see that after the acceleration time has passed, the voltage goes within the acceptable range. Right? Another example can be the motor sleep or motor speed, right? Which in this case we can actually use the transient stability case. Let's say that we want to flag or we want to generate the plots for those motors which sleep is greater than 5% or even greater than 10%, which usually indicates that the motor has gone to a stalled situation, or basically it hasn't started, right? Due to the torque equilibrium between the accelerating torque and the actual load torque, the actual motor torque, has produced this motor to stall and operate in a speed that is basically not its rated speed. It's not efficient to operate a motor at that point. That's why we need to actually generate and check one of those conditions. And as can be seen, it is right now being flagged by the UDM scope plot view that one of the motors that we started during the transient stability motor starting case actually didn't get to its rated speed, to its rated sleep. As we can see here, it's being flagged and it stabilizes at around 47% of the speed, which means that this motor could not accelerate. Maybe we need to take some other measures, reduce the load, or maybe upgrade the motor, get a bigger motor if that's possible, if we are in the design stage of the project. But this is what the UDM scope plot view allows you, instead of having to check hundreds of cases, hundreds of motor, hundreds of plots, by simply enabling one of these filter capabilities. Additionally, we have other filters too. For example, the voltage. Let's say we want to analyze for a transient stability study a bus voltage range between 110 and 82% minimum for all the different cases that we have studied: voltage impact, motor starting in transient stability, and so on and so forth. We can simply select all the available plots in the available plot data, and through the analysis tab, enable the filter, click on plot selection, and the result shall pop up for the violating plots. As we can see, again, for the motor starting case, we have only one bus out of 50, around 50 buses in our system that is basically violating that, and this helps a great purpose, as at this point we don't have alerts available in the transient stability module, but with the UDM scope plot view, you can simply enable the different filters and have a workaround for that feature. Before we move on to the last section or the last examples for today's presentation, we need to refresh a couple of items first. As we all know, in transient stability studies, different types of disturbances are modeled and analyzed to determine the ability of the power system to return to an stable condition after such events. One of the results that we usually keep an eye on during this type of studies is the rotor angle. After a disturbance, the rotor angle of the system machines should remain within a specific stability range. Once that angle exceeds the pre-established range, the stability of our system is compromised. Now, we will be able to detect this condition through the UDM scope plot view, as I'll show you in a minute with an example. Additionally, as we can see, transient stability results are always characterized by having signal oscillations. These oscillations can be of different shapes, magnitude, and time, and one of the main players on these oscillations is the damping effect, represented in elements like the damper windings of our synchronous generators and motors, or simply the inertial mass of big machines in our system. And those elements will play a crucial role in the determination of the system stability. Some of the different damping conditions are shown on the slide. The first one, not necessarily one that we would like to experience in power systems, as it represents an unstable behavior, which is undamped, followed by another undamped signal, which, even though it's not unstable, it is not a desired response when it comes to transient stability analysis, since, as we mentioned before, during transient stability analysis, we're mainly focused on the capability of the system to return to a stable operating point, which is basically what we see on the first item of the next slide, categorized as underdamped. This is the type of signal or response that we are targeting for this type of studies. However, we still have a couple of other conditions that are also important, like the critically damped, which, although mathematically feasible, its physical behavior might not be for most of the power system equipment. And last, we have the overdamped condition that might represent a correcting signal, but with a very sluggish reaction time, which may lead to other issues in our system, such as under voltage or under frequency, while it stabilizes. For this reason, we've added the capability to the UDM scope plot view to quickly detect some of these conditions after running the studies in transient stability with UDM scopes, or UDM models with UDM scopes, and allow you to analyze the results and take the proper measures in case of any stability issue. Now, coming back to our test system, we're going to analyze a fault case for which we'll have to determine the critical fault clearing time, which is a typical item during transient stability studies. So while ETAP is running, we need to go to the UDM scope plot view and select the actual plot database from the case that we have just run. Once we have uploaded the plot data, the critical fault clearing time will be determined with the help of the relative power angle filter available through the analysis tab of the tool. And we're going to have a typical range between 90 and negative 90 degrees, out of which the relative power angle might lead to unstable conditions in our system. So once we have enabled the filter and established the typical range or the required range for that angle to be after the fault condition or after the disturbance occurs, we can simply plot the selections, and we can see that there are two machines in our system, one of the synchronous generators and one of the synchronous motors, that are going beyond that range. Therefore, the stability of our system can be compromised, right? So the solution in this case, after we have applied a filter and the tool has analyzed hundreds of plots, is simply reduce the fault, which for this case was set to 450 milliseconds. So now we can simply reduce that to maybe 150 milliseconds and just rerun the scenario. Now, after the scenario is run in ETAP, we can simply go back to the UDM scope plot view, and with the same pre-established range, stability range for the relative power angle, click on plot the selection, and now we receive this message: no plot meets the analysis criteria, which means that for the filter that we have enabled right now, all the relative power angle or the relative power angle of all our machines is within the stability range that we have predetermined. If we reduce this stability range, let's say to 10 and minus 10, we can see the actual results from our system and how the synchronous generators are now between a much more stable operating condition after the fault is clear at 150 milliseconds. So we can say that we can determine and establish that the critical fault clearing time in this case, it's around 150 milliseconds. And now, for the last example of today's presentation, we're going to be analyzing a load shedding or load rejection case. And we will be paying special attention to the synchronous generator response after such event, specifically to the governor, prime mover or governor system, for which we have simulated a UDM model. While we check the UDM model, we can start running the simulation and check the UDM model. We have added several scopes so we can actually check the internal signals of the transfer function. And we're going to analyze the stability of the system based on the response of such UDM scopes. So now that the simulation is finished, we can simply go ahead and select the plot data for which we need the UDM scopes. We can clear the selection so we could have a clean list of plots. So we have all the plot data that we're getting from the scopes, from the internal signals of this governor transfer function, and once we're going to determine the stability of the system through the damping conditions filters in the analysis tab of the tool. Okay, first it's going to disable the relative power angle filter, and let's increase this setting. We don't want to be so strict about it. So now that we have selected and we click on plot all, we can see how the undamped condition is bringing two plots that are certainly matching with the description of the undamped simulation or undamped signals, right, which are not stable or are not desired for transient stability analysis. And the reason is that when checking the overdamped condition for our plots, we notice that the output from the mechanical power of this generator is overdamped. The reaction time of that controller for the turbine and the governor system is too slow, right? That's the first hint or clue that we received from the analysis done through the UDM scope plot view. So we can go to the UDM model for the governor and notice that one of our time constant is extremely high, right? Which probably is causing the instability in our system. So once we reduce this time constant, which is logical to have a much faster or lower time constant for a turbine, a gas turbine, we can simply compile the model, rerun the calculations, and open the UDM scope plot view once the simulation is finalized. And notice that no plot meets the criteria, which means that there is no overdamped signal, internal signal for the governor model, and there is no undamped signal. Therefore, if we disable the plot filter and go and check the actual response from our generator, from our governor, we can see that the response is not stable, is showing an underdamped condition. Therefore, there is no need to be flagged by the UDM scope plot view because the system is stable. So we can see that now with the help of the different filters for the damping conditions, we were able to quickly identify a potential stability issue in our system, and we were able to fix it and verify that the results were correct after running the transient stability simulations. To summarize, as seen in today's presentation, the UDM scope plot view is a tool which can help us to perform parameter estimation or parameter tuning based on comparison against field measure data, and it also provides many capabilities to arrange the way the data should be displayed for different studies. And last, it also provides multiple capabilities beyond what's being presented here, which include analysis filtering and further signal analysis comparison that can be customized through the different options in the UDM scope plot view editor. Thank you very much for attending this webinar, and we look forward to seeing you in our upcoming technical webinars.